Put again the reminder about the new time of the supplementary lecture, which was moved from Tuesday to Friday, 10 to 1. And what are we doing today? Today we are just, after we understood what impurities, what's the roles that they play, we'll try to understand how to calculate actually the number of electrons and the number of holes in the system once we have impurities. So the general model remains the same. We have a conductance band, we have a gap, we have a valence band, and the new ingredients in the game are basically impurities which add us levels for donors and acceptors. So we saw that we have donor states which are a bit below the conduction band. Why are they a bit below? Because they are still attracted to the positive center there. And we have acceptor states which are a bit above the valence band, and we want to see what happens to the occupation of the states in this situation, what is the influence of temperature, and see actually the further step is what happens if we have regions that have only donors or only acceptors. Okay. In nature, what happens? We have all kinds of impurities, and if we are taking just a piece of semiconductor that we find in nature, it will have both. In technology, you'll have only one of them because there's no point in putting them both into the same system, and we'll understand it a bit better further on. Okay, so what is the occupation of a donor state? Here, the blue states. Okay, this can have one of four states. We can either have zero electrons on this donor, Y, for example, moved to the conduction band, can have one electron which can be in one of two states, either up or down, because electrons have spin, or two electrons. Then it must be an up and a down. Okay. We'll forget about this state for the simple reason that costs a lot of energy. to push two negative electrons into a region where you have only one positive nucleus charge. Costs a lot of energy. You don't have to worry about it. It's much larger than the energy scale that we're playing here with here regularly. Okay, so I have three states here. So now we'll do statistical mechanics for a system with three states. So basic statistical mechanics with some overall states, which in this case is simple. We have only three states. Ask how many electrons exist in each state, and divide by the normalization. Those of you who remember something about statistical mechanics, that's this is just probability. Okay. And what ensemble is this?
Grand canonical.
Grand canonical, of course, because electrons can come from all kinds of places in the system. There's no conservation law about the number of electrons that exist on these impurity states. They can move somewhere else or come from somewhere else. Okay, so I'm just plugging in the different cases. Okay, if I have 0, nj is equal 0, this in the top part I have nothing. Then I have two states that each of them are filled by 1, so I'm writing 2 times 1 times E minus beta. The energy here is ED. If I have an electron, the energy ED minus mu. That's the top part. The lower part is if I have here 0 electrons, so N and E are equal 0, so it's 1. And I have, again, two states which have the same energy because spin doesn't play here any role. And organizing whatever I have here. So that's a probability of having, not probability, the average number of electrons that live on one donor. I want to know how many electrons exist anywhere in this donor band. I multiply it by ND. So the number of particles that live on the donor levels is the number of donors times the probability of a donor being occupied
May I ask a question?
Sure.
The number n, the big N T, is the number of electrons in the level of donors, or
No, the number of donors. We know that each donor, well, we assume that each donor can give up to 1 electron.
like an atom with electrons?
What is a donor? An impurity with 5 valence electrons.
And in the energy of donors is where all the electrons sit, or the imperfections?
Well, now you can ask an interesting question that we won't go into. These donors sit somewhere in the band, in the semiconductor, right? The average distance, we assume that the number of donors is small. So they sit far away from each other. So I assume that there's no direct tunneling between one and the other. Therefore, all of them sit on the same value of energy. They're as if you have ND independent states in the system. If, and that happens sometimes when people create materials, if it's a high number of impurities, you have to start worrying about tunneling from one to the other, and you know already what this will do. What will it do? It's a question to you. Think about the tight binding model.
Tunneling, maybe?
Yeah, of course, there will be tunneling, and what will it do to these levels?
And separate them?
Will create a band. So sometimes you can go into the literature of semiconductors, and for heavily doped semiconductors, you'll see a reference to an impurity band also. Can happen, but for the games that we're playing now, we assume that they don't talk with each other. You have just ND levels that all of them are in the same energy ED. Okay, we can go and play the same game for the acceptor level. Okay, what can happen in the acceptor level? The occupation then will be can someone explain what are the 3 levels that are in the game here?
Maybe one of them in 2 of them you have 2 particles. No, you have one of them in one particle, another one with 2 particles.
I have 2 states with 1 particle. With up or down 1 electron gives me n equal 1 times 2. And 1 state of 2 electrons.
Isn't it holes? Because we're in the center.
In a moment I'll translate, but here I'm just writing for electrons. If an electron is occupying the state, what will be the energy? And in E acceptor you have to have 2 electrons in order to get the level of the acceptor.
We said that in acceptor, the particles that are free are holes.
Wait a minute. That's a translation. On the basic level, what is an acceptor?
Someone who is missing it.
Someone who's missing an electron. I put in 1 electron. So it's as happy as any other electron in the band, right? Therefore, it has no contribution to energy, but has some contribution to from n times mu. If I put in 2 electrons, it already costs energy above what I want. And here it's n equal 2 and EA. So the same games that we did before. In a moment we'll translate it into holes.
So why don't we consider the spins in 2 electrons?
I consider I put here
In 2 electrons.
because it's only this way. You have only 1 condition in which you can't put 2 in up because they can't sit on the same level, right?
But they are not on the same level. One is.
I have the 1 electronic level open for them.
So where does another additional energy come from? When there are 2 electrons.
Let's go back here. I have 2 states with 1 electron that each one can be up and down. And here you're asking what happens to the spin of the additional electron, right? Before you added it, you had 3 electrons in the atom. 2 of them will be spin up and down, just to catch the lowest level in the valence of the electron. And the next one will be either up or down. But depending on him, it defines
Another one was missing.
the energy of the next electron coming in. Okay, so now I'll translate it to holes. That will be 2 minus n. And doing the arithmetics, I'll end up with PA equal NA. Okay, so we have ND number of electrons on the donor levels and PA number of electrons on the acceptor states. Okay, so in general, if I want to write what happens here from the point of view of number of electrons in the system, okay, electrons in the conductance band or on the donor states should be equal to the difference between the number of donors and number of acceptors. Think on the simplest case where you have no acceptors. So you have a certain number of electrons that these donors come with. But there could be additional electrons that get there because they left the valence band or because they left the acceptor band. So this is just a statement of balancing your electron numbers. They have to come from somewhere. Basically, they come either from moving from the conductance to the valence, or the fact that I have more donors than acceptors, and that's it. That's the statement here. Now, one can come and ask what actually happens to mu here. So, in general, mu doesn't move much. If I didn't have donors and acceptors, it would have been in the middle. If the number of acceptors or donors is not huge, it won't move much. I haven't proven it, but I assume it. Let's see, let's come out and check under these assumptions how the behavior of the occupation behaves. Because as you see, mu comes in everywhere. So I'm considering here low enough temperatures, so ED minus mu is larger than KBT, and mu minus EA is much larger than KBT. What it means that mu is still somewhere in the middle, consistent with our previous assumptions, for the case that we had a pure symptom. Okay. At the end of the day, the change between the number of holes and the number of electrons, or number of electrons and number of holes, just out of this. Takes the total number of electrons, subtract the total number of holes, and as for the pure case it would have been 0, here it's not 0, it depends on the difference between the number of donors and the number of electrons.
This is number of holes, right?
This is the number of electrons.
Okay.
Okay. We treated exactly this situation where we called it delta Ni. You remember in the previous lecture, we just called it delta Ni, the intrinsic difference between the number of holes and number of electrons, where we didn't specify from where it comes. But everything that we said in the previous case remains, so I just have to copy our results for delta Ni and substitute delta Ni with Nd minus Na. So here I need my color scheme. Same as we did in the previous lecture. So, we have here two situations. Nd minus Na is much smaller than Ni. So, in this case, Nc or PV will be equal to Ni plus minus half Nd minus Na. And the more interesting case, meaning that most of the contribution comes from the impurities, which is the usual situation. So I have two cases. If ND is much larger than NA, then NC is equal simply ND NA. And I have a negligible number of holes. Or if I have much more acceptors, then PV will be this is just a result of what we have written here, but what is the physics? The physics is extremely simple. If I have much more donors than acceptors, from where will the additional electrons come to the conductance band? They won't come from here. It's just too far. We said the temperature is small. Jumping from here to here is negligible. But jumping from here to here is probable. So any electron that comes into the conductance band will come out of the donors band. And actually we can forget about anything that happens here. And vice versa, if we have a lot of acceptors, an electron won't jump from here to here or from here to here. We'll just jump from here to here, and the number of holes in the valence band will be essentially the number of acceptors that we have in the game. Okay, now p-n junctions. What is a p-n junction? At the simplest level, it's a semiconductor that half of it is filled with acceptors and half of it is filled with donors. So if I plot here the conductance band, the valence band, top of the valence band, EA. Donor with some number of donors or density of donors. Okay, that's a p-n junction. Why is it a p-n junction? Because if I look on this side, very far from the boundary between the two regions, here I'll just have holes due to the doping, because as we said, it won't jump to here. It will jump from here to here and leave a hole, and this number of holes will be roughly NA. Okay, what will we have here? Here we'll have many electrons because they'll come from here and jump. I don't want it here. I want to. So very far away, we know this is an n-doped semiconductor, meaning that we'll see a small number of electrons in the conduction band. We'll do the Hall effect. We'll see behavior of electrons that are carrying the charge. We'll look on the left side, we'll see holes carrying. What happens at the connection between them? Here we have an interesting situation. Let's ask what an electron that color that sits here will do. So if I don't think much, say, oh, we'll jump to here like any other donor case. But this electron looks to his left, says, wow, there's a very nice level that is empty to the left of me. Let's go there. So this guy will move to here, and his neighbor will move to here, and so on and so forth. So here I'll have a hole, here I have a hole, here I have a hole. Will that go on forever? Meaning, will I empty this whole band?
No.
No. Why not?
There is a finite amount of holes.
No, it's not because of the finite number of holes. That's what I started. Will I empty all the holes into this part? No. Why? Because I forgot an effect here. I'm leaving positive charge, filling this up with negative charge. What happens when I separate positive and negative charge?
The potential equalizes.
I create a potential. It costs me energy. The first will go in easy, the next one less easy, and so on and so forth. At some point, it becomes already worthwhile to jump to here instead of jumping from here to here and paying all this potential energy to do it. So, very crudely, I'll have here four different regions. One region which is from infinity till here. The game is played as usual. Holes are created in the valence band by charge jumping into the acceptor. At some distance, I'll call it dA. I'll start already to see charge accumulating on the acceptor levels, not from here, but from here. I'll get to the boundary. I'll have here D donors, or sometimes you use D negative, and where I'm creating holes on the acceptor, on the donors, due to the transfer to the acceptors. And from here on till infinity, it behaves the usual way. Holes are created by jumping into the conducting space. They won't jump into here because the potential energy is too high. So we have a region where it behaves like a regular P or N doped semiconductor, and a region where it behaves differently. And this region is around, now what we would want to know, what is the thickness of this region and what is the influence of this region. That's our aim in the following couple of lectures.
So you are saying that only this area is where you have all the interaction, right? Because after that, there will be no more interaction between these two levels?
After that, I can't lose electrons from here to here. Although the level, if I'm just looking on the level, this state is lower than this state, I forgot to take into account the potential energy.
So this graph is not completely accurate.
This graph doesn't take into account the role of the interaction.
So the ED can actually go higher than the...
Wait a minute, I'll redraw it with a different notation.
And before this thing happens, that we can no longer lose electrons to the red, could the process of transmitting electrons from the blue parts to EC still happen in the meantime?
You empty a certain number of donors from here to here. They have to be close because the farther out you're paying more potential energy. You don't want to do it. So a finite region of here, this is located here. And how far and how does it depend on the parameters of these semiconductors is our aim in the following lectures. Now, why is this system interesting technologically? Because, and we'll show it in details further on, we'll do actually the calculation. This guy can move current in one direction, but can't move current in the other direction. So we have here basically a rectifier. Rectifier basically changes an AC current into a DC current, because if you're allowing putting in as an input an AC current which sends the current in both directions, and put an element that lets you move only in one direction but not in the other direction, you change the sign into just a bunch of humps, and that's DC. Why is that so important? It's a basic ingredient of any radio transmission. Basically, you can have a radio receiver with no transistors, but you can't have it without a diode. So what did they do in the 20s and 30s before people understood semiconductors?
Codes and codes to one another that they could just read like
No, people actually, I don't know how many of you played this game, probably no one here. The 20s and 30s it was very popular. Further on died out just because we have more sophisticated games to play with. To build a radio receiver, what do you need?
transmitter,
Receiver. You don't need a transmitter for. All you need is an antenna, meaning a long piece of conducting wire.
You mean that phone thing that has a rope between it? And
No, that's not an electric device. I'm talking about something that can actually detect electromagnetic waves and give you sound. So all you need is an antenna, a diode, and an earphone, this small something that changes current into sound. From where did they have diodes? Okay, so people who had a lot of money built such a device out of vacuum tubes. Something that looks like a bulb. It has a cathode and anode that sends out signals, and you have in the middle a mesh that you can charge with voltage that stops it from moving from one side and allows it to move to the other side. So that's the traditional diode. Now, this is expensive, like all the old bulbs, prone to burn out. Sensitive because it's glass, and if you have some vibrations or something, it breaks up easily, and expensive. So it turned out, and amateurs knew it in the 20s, you could take a piece of semiconductor, connect two wires into it, play around, and get a rectifier. Why did it work? Just because in a natural occurring semiconductors, sometimes there are areas of the semiconductor which has a large number of acceptors, another area of donors, and if you were lucky enough to stick your wires in one and the other parts of this semiconductor, you could get a rectifier for free. This was much cheaper than using a purpose-built vacuum tube, but you needed luck and patience. Luck to get these areas and patience to find out where they are. So when AT&T, the big American telephone company, wanted to make cross-country telephone lines, needed a lot of rectifiers, and it became extremely sensitive just to maintain points where you have these rectifying along the telephone lines every 50 or 60 kilometers. The US is a few thousands of kilometers, so you need a whole technical apparatus to check and maintain all the. They knew that there is something that can replace it with semiconductors, and they had the goal of doing it. That's why Bell Labs, which was a research laboratory of AT&T, was so interested in physics of semiconductors. Just because they knew that it naturally occurring materials seem to give you the functions that you're interested in, but nevertheless, you didn't know how reliably to put it into a device. Nobody wants a phone that each morning you have to start sticking wires and see if you can find these patches. And they started much before World War II. All research in this area stopped because the people that were in this research were taken to other projects, and once they came back in '48, they came up with the transistor, basically. So our aim is to understand what happens here and why this is a diode, why current goes from one direction but can't be transferred from another direction. Okay. So, our main conclusion is it's not enough just to look on the energy levels without taking into account the electric potential, right? Because otherwise you'll just get all the electrons from here to here, and that's end of story. So actually, let's plot 5 peaks on the same diagram. So, what is phi of x? If we remember something from our high school lectures, basically it's the amount of work that I have to do to move a positive charge. So, I have some value here, phi minus infinity. Until here, these two guys just cancel each other and it remains phi minus infinity. So it doesn't cost me more energy to move it along the way because there is no electric field. Here there's already an electric field, and to push it towards the positive part already costs energy. And here again, I end up with phi plus infinity. So I have more or less such a profile. Say more or less because we will actually calculate phi of x. And now, what is the energy that costs us to fill up an electron or a hole anywhere in this game? Well, let's use the definitions that we have defined in the previous. NC is equal to capital NC. You remember that we defined it in the previous lecture. So what did we change? In the previous lecture we had no phi x. Here we're adding phi x to the constant energy. Same for the number of holes. And of course all of it has mass. What else do we know? It's the same thing that we did in the previous lecture, just adding the potential and a different sign because these are electrons and these are holes. What else do we know? Well, we know that the boundaries NC at infinity is equal to MD. PV at minus infinity is equal to NA. As we argued, very far from this boundary, we return to the usual behavior. So, How did I do it?
Divided the equation, then did the on both sides.
Exactly. And since mu is defined the same way all over the system, the same. So I just enter the value at infinity and minus infinity divided by each other and got this connection. It's nice because I have no mu now in the game. My problem is always in these types of statistical mechanics calculation to calculate mu. That's usually the stumbling blocks. It's the thing that is harder to do. Here we avoided it and we get a very interesting connection. We know a connection between the difference in potential, because this is basically the potential difference between the two edges, and all the parameters of the system, EC, EV, and numbers of donors and acceptors, and the intrinsic NC and PV, which is results for clean semiconductors. And instead of writing it in this way, EC minus EV is just the gap. So tell me the gap, tell me the number of acceptors and donors, and tell me the properties of the clean semiconductor, and I can tell you what is the potential difference between both ends of the system. Now, some people, instead of plotting phi in this game, prefer to plot, to say I have a mu which depends on location. I find that confusing and not a good language, because mu should be a global parameter of the system. I'm just saying it so if you ever run into some textbook, Ashcroft actually brings it, you'll understand what it means, but anything you can do in this way, you can do in the other way, so no point in repeating it. Okay. So, our aim is understanding this behavior. We have to give a functional value of phi x everywhere in the system. I know the difference, but I don't know how it behaves exactly here.
Wait, how does this relation count here? It comes here in this graph.
I just take the two equations up.
Divided them and then into the line, but where does it appear here on the graph? That's what I'm saying.
Phi minus infinity, phi plus infinity, EV, ED, sorry, EV, EC, and
okay,
the number.
it's not the behavior of the graph. It's just the.
This I've just drawn by hand. I didn't give it an exact behavior. That's what we are going to do now. Because till now, said it makes sense if it goes from here to here, And here you have no charge, no energy, electrostatic energy paid for going from here to here. That's all I said.
Because until that point, nothing transmitted. That's what you're saying.
You have no charges here. This is electric-wise neutral.
Yeah, you mean until that point, everything is nothing. That point and on is
I start to have accumulation of charge. I have accumulation because these are nucleus that want to have on them only 3 electrons, and they have now 4.
So now they do have a charge.
They have a charge, so this region has charge. If you remember, the main lesson you have to know about electric potential is where you don't have electric fields, it doesn't change, and where you do have electric fields, meaning charge, it does change. That's all. If you want a very, very, very simple analog for the system, think about a capacitor with 2 infinite. Here you have negative, here you have positive. Phi changes only in between them, but not out of this region. If you have such a system, this is 0, 0, and well, you have to define. You have V and here V. It doesn't change. Anywhere else. Seem confused. Do I need to explain the capacitor?
What do we get a capacitor? I mean, we have no.
It's an area of pluses and minuses, so I simplify it to 2
Yeah, okay, I see.
infinite regions that are charged. So of course not the description and not what we'll do here, but that's just an analog.
You're right to be both in the middle and the right side.
Because I'm taking a charge here. If I assume that in infinity it's 0, so and to bring it to here doesn't cost me energy. From here to here I have an electric field, so it costs me something to move it from. So it's V. And then I paid V, so anything that gets here I'll have to pay V to bring it from here. So it remains constant. Constant V is like constant energy. What's interesting is a change in V to define the work. Could define this here as 100 V, and here it will be 101. Doesn't matter. Just setting.
No, so it's constant and equal.
Okay. So, from where will we get phi of x? Well, here we move a bit beyond the high school electrostatics into beginning of university electrostatics. Poisson equation. Since I have the charges upward, in principle I should be able to calculate the Poisson equation and conclude what is the electrostatic potential here. Okay, so what's the charge density? Whatever charge is sitting on the donors plus whatever charge is sitting in the conductance or valence bands. Well, to be consistent with minus NA plus minus S. Okay, so I wanted to change the notation of the distances, so this I'll call dN and this I'll call dP, just on the P side and on the N side, okay? So I'll come and do an extremely simplified charge profile. More or less by definition, for all the region to the left of my depletion, I have the simple case that just writing down what I said in words several times. Far from the boundary, all the acceptors accept electrons from the valence band and leave their holes. PV equal to NA. Not surprising, the behavior to the right, in this case it will be NC equal to ND. Yeah. Just a simplified assumption that from that point on, it's as if you have infinite semiconductor just with acceptors or donors. The interesting thing is of course happening in between. And as you see from the picture here I assume that almost all the additional charge comes into the acceptors or is left out of the donors, and I ignore what happens in the valence band and in the conductance band. Why? Because the majority of charge here doesn't come from here, it comes from the guys that have, you understand why? I have here huge energies that I want to spend by jumping here, and here I have to actually pay a bit of energy. So if I don't have from where to get a charge, I'll pay this additional small energy. But if I have here a reservoir of electrons sitting in much higher energy, all the electrons that are sitting here will come from there, not from the valence or vice versa. All the holes that exists here won't come from an electron jump to here when it can jump across the boundary and not pay energy but gain energy by this jump. So, what does it mean? That here the charge will be because simply MC and PV are neglected. Let's write it down. In a bit more detail. I assume that the doping is constant till the boundary. So to the left I have just minus Na, to the right Nd. Okay, so I know what's rho. I look on my Poisson equation, it's not, I don't need here vector notations, it's one dimension. So I have simply minus, or let's for simplicity already write just second derivative of the, yes.
לא כל כך הבנתי מה כתבת שם. הרי זה לא שהמיטה מתפלג, כאילו המסממים מתפלגים. זה לא שבכל נקודה יש...
No, it's naive till the point of almost crying for the naivety of what I'm doing here. I'm telling you, fills up, fills ups, and then stops to fill up. Okay, I say nothing comes from the valence. On the top side, nothing comes from the conductance. Okay, how many charge accepting locations do I have here? Number of, to the left, number of acceptors, to the right, number of donors.
סך הכל כמה יש בכל צד, זה לא כאילו בכל X.
Exactly, I'm telling you it has a constant level of doping and all of it is filled up. Why all of it is filled up? Look, this guy has a huge an energy disparity, so it will go immediately to here. Can't say that around the edges it will be somewhat softer, I ignore it. So, for x smaller than minus Vp, what would be the second derivative of the potential? Zero, of course, nothing else. Can't be anything else, no charge, potential doesn't change. If you want to be, put here 0 and the second derivative is equal 0. X between minus dp and 0 what will it be? NA, because of the minus, divided by epsilon.
Times E.
Okay?
Excuse me, so why between the dp to dn we don't have the NCMP way?
Where?
From the minus dp to dn, yes, why we don't have the minus nc plus p way this term?
Because I told you that almost all the electrons, you're telling me, hey, you forgot that an electron from the conduction band can skip here, right? That's PV, right? I tell you, why should I care? Because there's a much higher probability that it will come from here. Because this is a huge amount of too much energy, while here you have to pay some small amount of additional energy. Why not gain energy and finish the game? You are right that it will make some small difference here, but I'm trying to get the general behavior, not some small difference. Okay, I'll return to this game now with phi of x. Okay. If the second derivative is 0, the electrostatic potential doesn't change, and in this region it's equal to minus the potential at minus infinity, because it doesn't change anywhere along this change in position along this until I get to x equal minus dp. Why? Do a second derivative and you're getting what's written here. And that is just to stitch the boundary. What happens here? Okay, this is my plus infinity, and I'm stitching with this guy. Okay, the derivatives fit. The stitch between this guy and this guy fits. Stitch here fits. Doesn't fit. So we'll have to fit it. So what do I have to fit? I have to fit two things. The first derivative, sorry, and phi have to fit at x equals 0. Okay, how did I get these two results? Well, the first one, I just put here x equals 0, and they have to be the same at x equals 0. I get this relation. Remember that phi infinity minus phi minus infinity is delta v, which we have calculated. Perform first derivative and equate it, I get this condition. So, and this is the final for this lecture. So I got the lengths of these regions. In the next lecture on Friday, we will see what it means from the point of view of physics. Is it big, large, small? What is the order of magnitude of these regions? And what does it actually tell me about trying to drive currents through this junction? Okay, so we'll stop here.